So I work for a company called Cloudflare, where I focus on performance and efficiency of our products. I don't usually do public speaking, and I have terrible memory, so please forgive me if I look at the notes too much. So if you never heard about Cloudflare, it means one of two things. Either you own a website and we fail to inform you that you should totally use us, or you don't own a website and we're working well enough for you to don't know that we exist. We're a CDN with benefits, so in addition to traditional caching and DDoS protection and like bringing content closer to the user, we try to be the forefront of innovation with technologies like TLS 1.3, quick server push, edge workers. And the idea is generally to make internet the more secure and up-to-date for everyone, even if your origin server does not support these technologies. We're also the fastest authoritative DNS, and we provide privacy-oriented 1.1.1.1 resolver. So you should totally use that. And you should totally use that with DNS over TLS so your ISP don't see what you're browsing on the internet. And Prometheus and PromCon website also use us, apparently. Last year, my colleague Matt Bostock was here. He was talking how we do planet-scale edge network monitoring with Prometheus. And you can check the slides and the video. It's still useful. I'm just going to give a quick refresher on the numbers. So the only thing that didn't change here is the 10% number. And it's not exactly a scientific number. It depends on how you count the internet requests. Otherwise, we doubled in terms of HTTP and DNS requests. And DNS does not include the public 1.1.1.1 resolver. So that did grow by a factor of positive infinity. We're at 150 data centers instead of 100 just a year ago. And we plan to cross 200 this year. And each of those needs monitoring, and that's what we use Prometheus for. And our global Prometheus deployment did grow with our edge network. The numbers here are per Prometheus, so they're not for all 267 Prometheus services. And we're very much looking forward to having Dennis to manage this and keep this in check. So that's all great, but that's not what I was here to talk about. So I want to tell you about an exporter. So let's first have a look at what we have now. So there are two main exporters one can use for system metrics with Prometheus on Linux. So the first one is Node Exporter. It gives you information about basics like CPU usage breakdown by type, memory usage, disk I/O, file system, and network. The second one is cAdvisor. It gives you similar metrics, but instead of having them for the whole system, you get them with the container level. And systemd units are also containers for cAdvisor, so you get those as well. And with that, you can see like what's the breakdown of total CPU usage by actual end services. And this is absolute minimum of what you should have for your systems. And if you don't have those, you should probably start there. And I should mention that every screenshot on this talk is from actual production machine doing something maybe remotely useful. But we have different machine generations, so don't assume that every Cloudflare machine is just like that. So here you can see the basics you get from Node Exporter in terms of CPU and memory. You can see like how much is used, how much Slack resources you have to grow. Some more metrics from Node Exporter as well. Now for disk I/O, and there's similar metrics for network. And at the basic level, you can do some correlation. Like if you see that CPU went up, you can see did network go up, did disk I/O go up, that kind of stuff. Next. So with cAdvisor, it gets more interesting because you can see how global resources like CPU gets sliced down between individual services. So if CPU or memory growth for the whole machine, you can see which exact service is responsible. And if it doesn't grow for the whole machine, you can still see how it changes between the services that run on the machine. And all of this information comes from the simplest counters. You just take rate over them and you're done. So counters are great, but they lack details. So for example, in I/O, we get device time from Node Exporter, and the rate of that cannot go beyond 1 second per 1 second of real time. So you can get you get a bold red line at 1 second mark, and you can't go beyond that. So you know your limit and you know where you are. And that's basically the utilization you get. We get this one number, but that doesn't really characterizes our workload because it's simply not enough. Like, you don't know if you're doing many fast I/O operations, if you're doing few slow ones, if there's some kind of mix. So this question is back for a histogram, and like the counter is what we have above, and the histogram is what's below. And keep in mind that Prometheus histograms are inclusive, so all E label means all events below that mark. So imagine we have the histogram for disk I/O, and this is just to visualize the difference in details you get. This is the same event in two views. On the left, you have like just a simple counter. On the right, you have a histogram. The event is SSD replacement in production, and you can see the different shifts you get from that. In a new Grafana 5, you can see, you can get heat maps. You can get histograms visualized at heat maps, and so that's pretty nice. So the next slide has a bigger screenshot. Here you just see like difference in the amount of detail you get. So here you see like color-coded buckets for each time slot and distribution in the tooltip. So you can see like you get that many I/O operations in this bucket. It can definitely be better, but it's already a lot better than just one simple line you get from the counter. So in addition to nice visualizations, you can also plot a number of events below or above some line, and you can have SLO or alert in that. So you can like, absolutely cannot have IOs beyond 1 second, and you can get an alert. And if you're looking closely at the histograms, you may have noticed that vanish and y-axis are kind of high. And that was SSD. So before the replacement, you can see like the bucket from 0.5 second to 1 second. And the text specs give you that the typical I/O operations is 50 microseconds. So that doesn't really add, just doesn't live up to the spec. And this is, again, that's the kind of detail you get from histograms. So by now you should be convinced that you should have histograms for events like that. Okay. So if you wanted to switch your all of your stored latency measurements to histograms, I have bad news for you, because you can't with Node Exporter, because Linux only provides you with just one counter for each device, but still it's just one counter. You can try to mess with BLK trace, but that's not going to be fast, and it's not going to be practical, I think. So let's switch gears a little and see how summary stats for counters can be more deceiving. So this is the research from Autodesk. The creature on the left called Datasaurus. Then there are figures in the middle that are target distributions. And on the right, you have animations going from the Datasaurus to the targets. And the amazing thing here is all animations, each frame on the right has the same mean and standard deviation for every frame. So if you don't plot your data, you just don't know what's happening. So yeah, so from summary statistics point of view, it's all the same. This is from the same research. You can clearly see how box plots in the middle don't give you the amount of detail you want. And on the top, you see histograms, which is what you basically want. So we established that histograms is what we need. But you need individual events to make those histograms. So what requirements would you need for a system that gives you, that handles that? Assuming that you want more stuff than just I/O operations on Linux. It has to be low overhead, otherwise you can't run it in production, and that's what you want to run it. It has to be universal, so you're not locked down into just I/O tracing. Like there are plenty of things you can measure on Linux kernel. And it has to be supported out of the box, so third-party modules are not very practical for that. And finally, it has to be safe. It's not really fun if you crash a kernel across a large chunk of the internet. Many people won't be happy. Probably you won't be. So it turns out, and there's a solution, it's called eBPF. It's a low overhead sandbox user-defined bytecode running in the kernel. It can have a crash hand or interfere with the kernel negatively. So that's kind of vague, but here are two links for you to dive into the details and explain how it works. So the main part here is that it's already included in the kernel. So you already have it. It's used in networking subsystems and stuff like seccomp for security and stuff. But the general idea is that you can run safe code in the kernel. It's way beyond just that. And I think sysdig is going to have that as a backend for their tool as well. So you won't need a kernel module to run sysdig. So the previous slide said it's a bytecode. This is how it looks. So the good part is that you'll never have to write it by hand and maybe never even see this scary stuff. So to use eBPF, you write small C programs that attach to kernel functions and run before or after them. And your C code is then compiled into bytecode, verified, and loaded into kernel, where it runs with JIT compiler and translated into native opcodes for your machine. The constraints of the code are enforced by verifiers, so you're guaranteed not to be able to write an infinite loop or allocate a lot of memory, which is great because people are generally not good at writing code. And to share data with eBPF programs, you can use maps. So in terms of metrics collections, you update maps in the kernel, and then you fetch the values from this map in the user space when you scrape metrics. And it's critical for performance that eBPF VM runs in the kernel, and it never does any syscalls because, well, you're already in the kernel. And you can see the workflow on the image down here. So having to write C code is not an eBPF constraint. You can produce bytecode in any way you want, like you can write it by hand. You can use another language like Ply or Lua, or like sysdig can do it now. And maybe someday people will be able to write safe JavaScript in the kernel. That sounds scary, but just think about it. So just like GCC compiles C code into machine codes, BCC compiles C code into eBPF opcodes for load in the kernel. So BCC is a rewriter plus LLVM compiler in a library. So you can use it in your code. There are bindings for C, C++, Python, and Go. And in this example, we see like a simple function that runs after dlookup kernel function that's responsible for directory cache lookups. And it doesn't look that complicated if you look at it sometime, especially if you understand how C languages work. In addition to compiler, BCC includes some tools that can be used for debugging production with low overhead. eBPF provides. So let's quickly go over a few of them. So this is biolatency. The bio here doesn't mean biology, it means block I/O. And show you a histogram of disk I/O operations. And that's exactly what we started with, and it's just in a different form. It's a script instead of an exporter. This is exec snoop. It allows you to see which commands are being launched in the system. It's often useful if you want to catch something that is quickly exiting, so you can see it in PS output. Right. This is X4 slower, which is showing slow file system operations instead of I/O operations. So you may think that these two map together fairly closely, but one file system operation does not necessarily mean one I/O operation. For example, writes can go into write-back cache and not touch disk until later. Reads can involve multiple I/O operations to physical device if you read a large buffer. And reads can also get blocked behind async writes that you issued earlier. So the more you know about disk I/O, the more you want to run stateless, really. So it's just depressing. Okay, so now to the main idea of the talk. We have all these primitives. So we now should be able to tie them all together and get an exporter on our hands to get metrics into Prometheus and like graph them and alert on them. So many BCC tools already have kernel side ready, like biosnoop or biolatency, and they are reviewed by smart people that understand what they're doing, not people like me. So the hardest part here is covered. So the idea is simple. We compile BCC programs and load them with the exporter. The programs then run in the kernel and collect metrics we want them to collect. And on scrape time, we just pull. Sorry? Oh, I'll be quick. We pull them and transform keys into labels, and values just convert them to float 64 because kernel doesn't know floats exist. So let's look at the simple example to get counters for timers find in the kernel. The example is from eBPF exporter repo. When you can find more examples, more complex than this one. On the BCC side, you can define a hash and attach it to a trace point. And when a trace point fires, we increment the key. We can increment the map where the key is address of the function. And when we scrape, we convert this address into a function name with the map provided by the kernel. So this is the example graph you can get from it, and you can see like how it changes with the daily load patterns. Why can this be useful? You can check out the Cloudflare blog post about how we traced issues with timers when we did the OS upgrade. The TLDR is that systemd broke TCP segmentation offload on VLAN interface, and that increased CPU 5x and introduced interesting stuff like page allocation stalls. When you try to allocate memory, it stalls for like a minute, and that's not fun. So if we had metrics for this enabled, we would see it sooner. Another bundle example gives you IPC, which is instructions per cycle, for each CPU. So in production, you can see, in this production system, you can see a few interesting things like not all cores are equal. So the green line is core 0 and the yellow is core 1. So you can see like the green is on top and the yellow on the bottom, and the rest of the cores are in the middle. And that's because how we pin services to the cores. And there was some event that affected what looks like upper cores. So that looks like something that can be investigated. So why can this be useful? You can check out the Brang and Greg's blog post about CPU utilization. And the TLDR here is that CPU percentage means not what you may think it means. So in the picture, you can see if your CPU is that some percentage busy, it can mean that it just stalls on memory access instead of doing actual work. And you can see with IPC metrics what is actually happening. Another bundle example is LLC or L3 CPU cache hit rate. This is from the same machine as IPC metrics. So you can see like the same event happening, and you can still see like different cores have different patterns. And if you understand this, you can probably investigate. But if not, like you do a kernel upgrade and you see it changes, maybe go ask somebody. That's what I do. So why can this be useful? You can see how your CPU cache is doing, and you can see how it may be affected by bigger cache or more cores sharing the same cache. And that can be used as like as a purchasing decision. Do you want to like buy bigger CPU? Now to the fun part. We started with I/O latency histograms, and they bundled. This is also a histogram, but this is for run queue latency. So when the process wakes up in the kernel, it's ready to run. And if we have a CPU ready, it can run immediately, but if not, it has to wait. And this is measuring that scheduling delay. And you can see like, this was unexpected for me that you can wait for like 66 milliseconds to wait. And you can get the same metric from cAdvisor, but again, as a counter instead of a histogram, so you wouldn't see like actual distribution. I'm gonna skip over it, but this is actually useful. These are not only possible examples. You can have like 500 hardware events and counters on a typical system. There are 2,000 trace points and like 1 billion kernel functions you can trace. And this is from Brendan Gregg's BCC tools image, and it shows you what you can measure with what tools. And each of those tools can be converted into exporter to give you metrics for long-time investigation. But nothing in this life is free. And this even low overhead means some overhead. So you should be measured on your own environment. But this is what we've got. For fast get bit syscall, you get like 34% overhead, which sounds like a lot, but it's 100 nanoseconds. And I Googled what 100 nanoseconds is. It's one memory reference, and which means like just that get bit is very fast. For a complex example where you like make some randomness, read some memory, it gets to 100% overhead, but you can still do 1.5 million syscalls per second on one core instead of 3 million. So if you measure stuff like disk.io that you don't do 3 million times per second per core, then you're probably going to be fine. And for run queue latency, we saw 300 millisecond CPU increase, just 1 minute. And on a machine with 40 logical cores and 250 scheduled events per second, so that's visible, but still low. So we should run the exporter anywhere you feel comfortable, but complex programs can be gated to canary machines. At Cloudflare, we have canary data centers, where we have actual live users, but that's not as bad as it sounds because we test on ourselves before we roll out to these test users. And for upgrade events, you can roll it out on machines that experience the upgrade events. That's all the time I had. I even ran over. Thank you. You can use it, do it. There are more links. That's it.
Thank you, Ivan. Got time for 4 minutes. Questions?
Hey, thank you for your talk. I was wondering if if the eBPF program only writes into maps in the kernel, and then the user space program exposes that metric to Prometheus. How do you make sure that when the thing that you're actually monitoring goes away, that's actually cleared from the kernel maps, so that we're like not creating memory leak in the kernel?
Oh, so eBPF programs are attached to the process. Like you attach them from a process, and then when a process dies, they're removed. And the data. Unless you pin it, you can pin it and use it later, but we don't do it for exporter because we don't need it.
So you mentioned cAdvisor at some point earlier. Does this work? Like, can you export the label that's the C group you are attaching the probe to?
That is not something that's possible now, but in the future there are proposals to attach container ID to cgroup, because you have cgroups, you have other things that constitute container, and they don't always are visible for stuff outside of cAdvisor. So it's not possible now, but they're a work in progress.
Okay, thanks.
Two quick questions. One, does this require root?
Yes. Well, you have to attach in the kernel, so. I guess you can do it without root if you have sufficient capabilities, but I haven't tried it because we go deep in the kernel.
Right, that kind of invalidates the second question. It was if there was any idea of maybe putting some parts of this that are safe and very well tested into the node exporter.
So, I don't know. It's it can be later in Node Exporter, but I don't know if it should be, because it's a free form when Node Exporter is rigid metrics you get.
Ask the kernel people to expose more metrics.
Yes. Good luck with that.
Hey there, great talk. So can we run different trace points per one node exporter, or do we need to run several?
You can have multiple programs in one eBPF exporter. So we run block IO, we run scheduling, latency, we run timers, all in the same exporter.
But then can you mix kprobes and other micro probes as well?
Can you repeat louder, please?
Can you mix the probes that you're using in the same ABF exporter?
Yes, yes. You can mix them in the same. You can have different metrics from same eBPF exporter, and you can have one programs attaching to multiple trace points.
Okay.
Thank you for the talk. You said that the exporter compiles the code and loads it. Does that mean we need to install LLVM on the production machines?
So the LLVM comes in terms of a library. Mm-hmm. So the tool we use called GoBPF, and when you compile it as a dependency, it compiles into your Go binary as it just compiled in. You don't need the LLVM.
So another question, is that possible to load pre-compiled eBPF codes?
You can do it with the tool bundled with the kernel, but well, it's for different reasons.
Ah, okay, thank you.
You're really giving me exercise here.
Thank you. Have you run into any gotchas or limitations on the Prometheus histogram format as far as bucket limits or granularity in any capacity? Just because these tend to vary in scope, it seems.
Yeah, so you have to provide the buckets you want to see. And for us, if you do power of 2 up to a minute, that should cover everything. Many things won't go over a second in the kernel, but I/O is surprisingly bad.
Any other questions? Nope. Well, thank you very much,
Thank you.
Ivan.